Hello, we're going to get started now. So we don't have a final exam. We have one quiz this Thursday. Let me just tell you what it covers. So quiz, I think 5, it will cover 11.5 to 11.7. 11.7 is basically a review about all the tests that we have seen from chapter 11 up to 11.6. So that's what the quiz is going to cover, and then we have a quiz 6 next week. And exam 2 has been graded. I already upload the exam on the website, but I have not had the chance to type in the grades. So I will update the grade book sometime tonight. If you have any questions about the exam, the questions on the exam, you should let me know. Come see me during office hours. I'll be happy to go through those questions with you. Or if you have any questions about grades, please come see me during office hours. All right, and then the next Thursday, we're going to have a quiz 6, and then that will be the end of it. There's a homework, so let me just remind you, there's a homework 8 that's due Saturday. I believe it's Saturday, but I'm not sure, or Sunday, because I published the homework a little bit too late. But anyway, you should work on it now, because the material on the homework will help you with the quiz on Thursday. So you probably should at least look at all the questions before Thursday, so that you know what kind of questions will be on it, and then you can use it as a study guide. And there'll be another homework assignment I'll give you sometime later this week, and that will be due next week. Any questions on those? All right, if you don't have any questions, I'm going to get started. So the first thing I want to start talk about is factorials. You probably have, some of you have seen this before, some of you have not. It's good to review it, because some of the exercise questions that involving finding the convergence, you might need to know what factorial stands for. So definition, factorial is it's an algebraic expression. It's really a number. In the form of n with the exclamation mark. So that's called n factorial. So this is, we say it's n factorial. The n just integers. N is an integer. So that's n factorial. If you expand it, you can write as n factorial equals n times n minus 1 times n minus 2, and then times n minus 3, all the way to multiplied by 3, multiplied by 2, multiplied by 1. So that's what n factorial is. It's just a product of integers from 1 to n. A product of integers from 1 to n, or n to 1. So that's what n factorial is. Now here's a special case. Zero factorial. Of course, we're not going to multiply integers to 0, right? 0 factorial, we just define it as 1. That's a special case. It's the same thing as 1 factorial, which is just also 1. If you have 2 factorial, that will be just 2 times 1. If you have, let's just say 3 factorial, you can write as 3 times 2 times 1. And the good thing about factorial is that a lot of times we can change the form a little bit. For example, this 3 factorial is 3 times 2 times 1, but you notice that 2 times 1 is also 2 factorial, right? So 3 factorial you can write as 3 times 2 factorial. So that equivalent, instead of writing 3 times 2 times 1, you can write as 3 times 2 factorial. More commonly that we use n factorial, we can write as n times n minus 1 by definition times n minus 2. I'm going to skip a lot of numbers there, times 2 times 1, right? But this part, if we multiply from n minus 1, n minus 2 all the way down to 1, that really is n minus 1 factorial. Right, is you multiply integers from 1 to n minus 1. That's what we call n minus 1 factorial. So n factorial you can write as n times n minus 1 factorial, but the factorial only applies to n minus 1. It's not n times n minus 1 together factorial. It's just the second term. You can also write this as n times n minus 1 times n minus 2 factorial. And again, the exclamation part, it's applied to x minus 2. So n minus 2 factorial times the other two parts. And then you can continue to expand it. This allows you to simplify a lot of terms in a fraction. So that's a factorial. Any questions on that? If you haven't seen this before, just think about something factorial. It's really the product of integers, right? If you add the integers, you got like a sigma. You can use the sigma notation to condense them. But here we just use factorial. It's a review about the ratio test. So use ratio test to determine if the series is absolutely, so that's absolutely convergent or divergent. So the example I'm going to give is a series that's positive n from 1 to infinity, n factorial divided by 5 to the n. So this series, we want to know if it's convergent or divergent, and it's absolutely convergent. We're going to use a ratio test. If you recall the ratio test, if you want to use it, you have to find the an plus 1 term and the an term, find the ratio, and then take the limit. So we define L equals limit n goes to infinity of an plus 1 over an. That's what we define as L. And if L is less than 1, that will be convergent. If L is greater than 1, that will be divergent. And if L equals 1, that will be inconclusive. Right, so we just try to find the L there. But be careful, you always want to keep the absolute value sign. I saw some of you use the ratio test on the exam questions. It's not required to use, but if you use it, you have to use the absolute value under the limit. You cannot drop the absolute value notation. So here we have, this is what I'm going to call an. And the an plus 1 is just going to be n plus 1 factorial divided by 5 raised to the n plus 1, and that's in the exponent. So this is an plus 1. And then the next, I'm just going to define L. So L will be limit n goes to infinity, absolute value, an plus 1, that's an n plus 1 factorial divided by 5 raised to the n plus 1. And all divided by an, which is n factorial divided by 5 to the n. And from here, I'm going to use algebra to expand this part 5 to the n plus 1, that we can expand it as a product. So that becomes limit n goes to infinity. So I get n plus 1 factorial divided by 5 to the n times 5. And then the division, I'm going to turn it into a multiplication by the reciprocal, right? So that will be multiplied by 5 to the n divided by n factorial. And don't forget, we still have the absolute value. And then let's carry out this. So the next step is that I'm going to expand the n plus 1 factorial. So that's multiply number from 1 to 2 to 3 all the way to n, and then to n plus 1, right? But I'm going to expand it by taking out the n plus 1 term and then put everything else together. So that will be n plus 1 times n minus 1, and so on all the way to 1. But this part, that is just n factorial. So times n factorial. And then divide by 5 to the n times 5, and then multiply by a 5 to the n and divide by n factorial. So 5 to the n will cancel. Becomes just 5 on the left side, and the next fraction has a 1 in the numerator and then n factorial in the denominator. As you can see that after we take out the n plus 1 from the factorial, we end up with the n factorial, and then we also have an n factorial in the denominator. So those two cancels out, give us a 1. So we end up with limit n goes to infinity of n plus 1 divided by 5. And now if we take the limit, we end up with infinity. Right, the denominator is 5, but the numerator goes to infinity. So the absolute value of that goes to infinity. So this is greater than 1, right? So L is greater than 1. So since L is greater than 1, therefore the series that we're testing using the ratio test, it's going to be divergent. From the ratio test. Any questions about this example? I'm not hearing any questions. Let me know if you have any questions. So the next part, I'm just going to kind of briefly go through what the 11.7 is, and I'm not going to do any specific examples. Just kind of give you some ideas. So 11.7 basically put together all the tests that we could use to test a convergent or divergent series. So so this is for convergence or divergence of series. This is different. It's not about sequence. So be careful. This is only for series. Usually the easiest one will be the divergence test. Not always the easiest, but it's one of the easiest one. When you're given a series, the first thing you want to try is see if divergence test works. So to do the divergence test, let's see the series is sigma of n from 1 to infinity. We just take the limit as n goes to infinity of an. See if that's going to equal 0 or not 0. We want it to be not 0. So that will be divergent. If it's equal 0, we don't know. But we want it to be not 0. Sort of like an easy example, if you have something like limit n goes to infinity, well, not this. If you have series, which is, let's see, n minus 1 over 3n plus 5, or something like this. And immediately you can take the limit, right, very easily, because this part we have seen it so many times. If we take the limit, we know what the value is. And then we can see, oh, it's divergent because, you know, the limit is this number, or is it convergent because the limit is, well, not convergent. We can tell if the limit is 0, right? So if you have some example like that, so try divergence test. 2.
Sorry. So if the limit is 0, then it's divergent.
No, if the limit is not 0, it's divergent. If the limit is 0, we don't know. It could be convergent or divergent. But it's always, you know, if you have some expression that you just kind of like looking at it, you can take the limit of the an expression directly. Try this. And 2, so the divergent test is always give you, if it works, it always give you the divergent series. Right? 2 is the p series. If you want to use the p series test, you have to have the an to be 1 over n to the p, or some constant divided by n to the p. Or somehow you can like write it, looks like 1 over n to the p. So from here, if p is greater than 1, so that will be convergent. If p is less than 1, so that will be divergent. And the 3 will be looking at, see if it's a geometric series. And that usually has the an in the form of some constant a times some ratio raised to the power of n, or could be n plus 1 or n minus 1, doesn't matter, but it looks like a ratio raised to the power of n. If you have something like this, then depends on the r value. So if the absolute value of r is less than 1, that will be convergent. If the absolute value of I is greater than 1 or equal to 1, that will be divergent. Right. So those are relatively easy, like the p series and then the geometric series. You can just kind of like look at the expression that's given, like look at the form of the expression, and then decide which one to use. But the divergence test, you kind of have to take a limit, right, as n goes to infinity and go from there. And if those doesn't work, you might want to try other tests that's a little bit more complicated. For example, if you have something that the comparison test, which is if you have, I always think about if I have a fraction in this form in the sigma notation, and then I can drop one term to get a fraction that's bigger, or drop one term in the numerator to get something that's well, it depends on what the numerator is. It's addition or subtraction. You can just drop one term and get something smaller or bigger. You kind of have to look at the numerator and denominator there. If you have something like this, you can try the comparison test. Or if you have sine and a cosine, which you have seen on the exam, you can use comparison because just sine, we know, doesn't matter what it is. You could have anything here, any expression with n of n to the n or 5 to the n to the fifth, doesn't matter what it is, it's always going to be between 1 and -1. Same thing with cosine. So that's,
What if cosine was on the denominator?
what if cosine is in the denominator? You can still try to use comparison test. I'm not sure how effective it is because the denominator will be from 1 to -1. Definitely going to have a function that's a 1 with this numerator there because 1 is greater than cosine expression. So if you have 1 there, very like, yeah, you're going to have something like that. But the other side, if you have a negative, you got to be a little bit careful there because of the -1 there. So let me take it back. If you have cosine, you got to be very careful in the denominator because even though we know that cosine is less than or equal to 1, but once you put in the denominator, it's more complicated because you get a negative sign somewhere. You got to be very careful with when you put it in the denominator. Because if you have a negative value in the denominator, see cosine is -1/2. So 1 over -1/2 is not greater than 1. It's actually less than 1. Be careful there. Hopefully you don't see this case. I'm not going to put it there. Good question. Will sine and the cosine always be no, not convergent. So again, it could be divergent series. You have to use comparison to decide, because if you, for example, if I give you let's see. I might be wrong here. That's a good question, but I'm thinking if you have a sine n divided by square root of n, this one, that will be between 1 over square root of n and -1 over square root of n, right? And in this case, both of them, well, if I put in the series, let's just say the series is for n from 1 to infinity, right? Both of them, if we just apply the p-series test, you know that they're divergent series on both ends. So in this case, this expression, it's between two divergent series, then it has to be divergent, right? And I could just pick a similar example on this. What about sine n divided by n squared? Right? With sigma. So in this example, this series, it's between two convergent. So using the p-series test, this is a convergent. This is also convergent. So if you have a series that's between two convergent series, it's going to be convergent in this case. But the one on the left is divergent. So just looking at sine and the cosine itself, we don't know if it's convergent or divergent. It depends on the other parts in that series. Good question. So that's a comparison test. So if you see sine and cosine, sine squared, cosine squared, try to use comparison test, the direct comparison test.
I just had a quick question on that. So if there's a function that's bigger than the one we're looking at and it's convergent, does that mean that the function we're looking at is also convergent?
No. If you have a function, let's see some series, and that's bigger than this convergent series, right? That the smaller one is convergent, but the big one we don't know.
Meant the other way, like if an was greater than f of n.
Correct. So if it's the other way, then if the bigger one is convergent, the small one has to be convergent.
Okay, thank you.
Mm-hmm. And if so, the fifth type, you look through them, and then if you have a -1 raised to the power of n times bn, if you have a -1 raised to the n or n plus 1, n minus 1, so this tell you it's an alternating series. So you probably want to consider using the alternating series test. I'm not saying that that's the only test that you could use. There could be other tests that works, right? Comparison test might work. Could also be ratio test or root test. But if none of that works, you just want to find out the convergence, you might want to try alternating series test. The next one will be the ratio test. Some of you probably like to use ratio test more often than others, but this is a very useful if we have factorials. If an has factorials in it, or just a constant raised to the power. If you have those expressions, it's probably good to try the ratio test. But again, other tests might be easier. For example, if you have, we saw it earlier, if you have a series that's 3 times 4/5 to the n, even though it has a number raised to the n, but if you use the geometric series test, it's a lot quicker than ratio test. And then the root test, it's useful for if you have a series that has some constant a times b n raised to the power of n. If you have something like this, you might want to consider the root test. So that's sort of like the key there, to have some n in the exponent. And then when you take the nth root, that exponent goes away, make it easy. If that doesn't work, you might want to try the integral test. I'm not saying that you have to go down the list, right? 1 to 8. You kind of have to, based on experience, look at them, see if it's like one of the easier case. If not, sort of go and try the comparison, try the ratio or root test. Any questions on those? This is 11.7, so just basically put together all the tests that we have come across in earlier sections. All right. Any questions? So if you work on the homework questions, if it says specifically use the ratio test or the root test, then you just stick with the specific test. If it doesn't say anything, you can look around, see whichever is the easiest one. Not seeing any questions, so I'm going to move on to the next section. Hopefully it wouldn't take very long. So the next section, 11.8, is on power series. Power series is similar to what we have seen before, except that when we talk about those tests, we work with numbers in a series, right? Some expression that depends on n. If we plug in n, we get individual values in the series. But a power series is a little bit different. It involves the variable x. So it involves variable x. So by definition, a power series has the form, it has the form sigma n from 0 to infinity Cn x to the power of n, where Cn is just coefficients. And if we expand this term, we just plug in n equals 0, n equals 1, n equals 2. If we put n equals 0 there, we get C0, which is just a coefficient. X to the 0, we know x to the 0 is 1, just C0. Plus, put n equals 1, so we get C1 x to the first power, we just write x, plus the next one will be plug in n equals 2, so that will be C2 x squared, and it continues. So C0, C1, C2, those are just constants. So that's a power series, it just has x in it. And the more general form, we write as sigma n from 0 to infinity of Cn x minus a to the n, where a is a constant, Cn's are also constants. That if we expand it, we get Cn at n equals 0, that's a C0. X minus a to the 0 is 1, plus C1 x minus a plus c2x minus a squared, and it continues. So this is what we sometimes call power series centered at x equals a. So a is a constant. Right. So a couple notations. Because we don't know what x is, so since we don't know x, the power series, for example, this expressed this form, this power series it depends on what x is, right? It could be different. If x equals 1, we just get c1 plus c2 plus c0 all the way, to infinity, c infinity. We don't know it. That's divergent. But if we have x equals 1/3, you might get something that's convergent. So a power series could be convergent or divergent. It depends on x. So just if you're seeing a power series without knowing what x is, you pretty much don't know whether it's convergent or divergent. So that's a power series. And here's a couple examples. So the question is, for which x value, we're looking for x values here. For which x values does the series converge? So the series given is a power series. It has n from 1 to infinity of x minus 3 raised to the n divided by n. And we want this to converge, but we want to find out the x value that will make it converge. So we need to know the x value. How do we find it? Well, here, there's a few ways you can do it, but one way is to use the ratio test. We're going to assume that we are testing whether it's convergent or divergent. We're just assuming we are testing it, but at some point we're going to choose some x value so that it's convergent. So let's begin with the ratio test. So we're going to define L, which is limit n goes to infinity, absolute value. So that's very important to keep the absolute value sign. an plus 1, so that's x minus 3 to the n plus 1 in the exponent, divide by n plus 1, and then I'm going to divide by an, which is x minus 3 raised to the n, divided by n plus just n. I'm going to simplify the division in the absolute value. So that becomes limit n goes to infinity, absolute value, x minus 3 to the n plus 1, I'm going to write as x minus 3 to the n times x minus 3 to the first power. But you don't have to write the 1 in the exponent. And divide by n plus 1. And then multiply by the reciprocal of the denominator. So that's a n over x minus 3 to the n. Just like we seen in earlier example, x minus 3 to the n, x minus 3 to the n, they cancel. It becomes limit n goes to infinity of x minus 3 times n divided by n plus 1. Okay. So that's what L is. I'm going to take one more step. I'm going to separate the part that depends on n and the part that doesn't depend on n, because when we take the limit, only the part that depends on n will be affected. So I'm going to rewrite it as L equals limit n goes to infinity of absolute value n over n plus 1 times absolute value x minus 3. So that's why we keep the absolute value. So basically, we take out this part, which doesn't depend on n, we put it aside, and we add absolute value to it. And everything else, we leave it with the limit. And by doing that, we can actually take the limit of this expression. The part that depends on n, we just divide by n and take the limit. The part that doesn't depend on n just stays the way it is. So that becomes limit n goes to infinity of 1 over 1 plus 1 over n times absolute value x minus 3. And if we take the limit now, the 1 just divide by 1, just 1, and the 1 over n goes to 0. We get 1 over 1 plus 0, just 1. So we end up with x minus 3. So that's a L. Right. Now, remember, this is just a ratio test. We found L. Well, when is it convergent? When does it converge? It converges if L is less than 1, right? So recall that if L is less than 1, then the series converges. It converges absolutely, but here we just want it to be convergent. So that means if we want the series, we want the original one to be convergent, we have to force or choose, we have to probably choose. We have to choose that the L, x minus 3 absolute value, that's what L is by using the ratio test. We have to make sure that it's less than 1. Otherwise, it's not going to be convergent. So we're just going to say, okay, we're going to choose that x minus 3 to be less than 1. And then what is the x value from here? I don't know if you're familiar with this or not. So from here, you can write as x minus 3 is less than 1, or negative x minus 3. I always add the second case is when you add a negative sign in front of the absolute value, which is less than 1. And if you solve this, you get x is less than 4. This part gives you negative x plus 3 is less than 1. So negative x is less than negative 2. So x greater than 2. Which means, so we have x is between 2 and 4. So for any x in that part, the series that we are interested in, the given one, is convergent. So therefore, for x is between 2 and 4, the series, what was it? X minus 3 to the n over n, and from 1 to infinity is convergent. If x, say x equals 5, right? If we put 5 in there, that will not be convergent. If we pick x equals 3.5, then it will be convergent. So that's the process of determine if a given series is convergent or divergent. So that's what I do. I take a test, the ratio test or the root test, right? Take a test, assuming you just do the normal work, and then at the end, choose the condition for X that will make the series convergent. Any questions on this? Was signed previous question. All right, here's the second exercise. Again, we want to know the X value. So for which X values is the series convergent? And then the series is given is sigma from 0 to infinity of n factorial x to the n. Again, we don't know if it's convergent or not because we have an x here, right? We can't just determine the convergence. So we have to know what x is. That's exactly what we're looking for. We're looking for the x that will make the series convergent. So what we're going to do is that we're just going to apply a test. So again, it turns out that ratio test works well again. Try ratio test because we have an n factorial, then we have x to the n power. So I'm going to let L equals the limit n goes to infinity, absolute value, an plus 1 divided by an, so that's a n plus 1 factorial x to the n plus 1 divided by n factorial x to the n. And I'm just going to simplify the terms by expanding the n plus 1 factorial as a product and also x to the n plus 1 as a product. So that will be limit n goes to infinity, n plus 1 factorial is n plus 1 times n minus 1, so that's an n factorial, times x to the n times x. And the denominator is the same, not much we need to simplify, just keep it. And by doing that, now the x to the n we can cancel, n factorial we can cancel. It just leaves us limit n goes to infinity of absolute value n plus 1 times x. And I'm going to expand this. So that will become limit n goes to infinity of n plus 1 times x absolute value sign. Right? So now we can try to take the limit. When we take the limit, this first term is the only one that's being affected by n. If n goes to infinity, n plus 1 also goes to infinity. How about x? Well, we don't know what x is, but if we have infinity times absolute value of x, you can think about, is there any x that we can pick to make it less than 1 because we want it to be convergent? 0. Well, here you have to be careful because 0 is 0 times infinity. Is that 0? Or is it indeterminate? So you kind of have to decide there. It turns out that Daniel is right, I think. This is what I'm thinking. Even though infinity times 0, we don't know what it is, right? But we do know that if we have n from 0 to infinity, n factorial times 0 to n, well, 0 to any power is just a 0, right? So that, and then, so this part is 0, 0 times n factorial is always going to be 0. So that's always going to be summation of 0, right? So it turns out that this is less than 1 for only 0. That's the only value that works. It's not 1, it's equal to 0, right? Good point. Let me take a look at the notes. I feel like I'm misleading you with some of the examples here. The 0 to the power 0 to the 0 power is 0, right? But 0 to the infinity power, we don't know, or infinity times 0, we don't know. So note 0 to the 0 power is just 0. I believe. Double check. And the series that we have, if we were to expand it with the x equals 0, then we end up with, if we put 0 there, we get 0 factorial times 0 to the 0 power. And then plus 1 factorial times 0 to the first power. And then 2 factorial times 0 to the second power. And they continue, right? So all those terms, they all become 0. And then the 0 factorial is 1, 0 to the 0, I believe, is 0. So you get 1 times 0 again, that's a 0. So the second example I gave you, so the only value that works that makes the series convergent is just going to be x equals 0. That's the only one. any other values for x, it's not gonna make it convergent. But again, the idea is that you begin with something and then you try to force it to be less than 1. Any questions on this? All right, so here's a theorem for you. And this will be this theorem and a couple other things will be the last thing we're going to talk about today. So this theorem says for a power series, Cn x to the n as n from 0 to infinity, or more generally, you have x minus a to the n. So there are 3 cases, only 3 cases or possibilities. The first one is that this series converges only at x equals a. The second possibility is that this series converges. I shouldn't say only, there's just 3 possibilities for the man. The series converges for all x. So this is a for all. X. So converges for any x value, or it converges at a specific x value. And then the third case is that there is a positive number r that the series converges on the interval, converges if the absolute value of x minus a is less than r, and diverges if x minus a is greater than r. So those are the 3 possibilities when you look at a power series. The second example we seen, so the second example we had was series n factorial x to the n. That's this case. It only converges at the specific value x equals a. In that case, it's x equals 0, because you can think about this is the same thing as writing as sigma n factorial x minus 0 to the power of n. So a is 0 there. So that's converges at only 1 value. And the first example we have seen that converges over a range of x values. We had series x minus 3 to the n over n. This one we found out that it converges for x minus 3 is less than 1, right? So that's a case it converges. So that's a third possibility. We haven't seen an example for the second case yet, but those are the case. And we're going to go through a couple examples on this material. soon, but there's a couple of definitions. So note the R value we saw in number 3. So R in number 3 is called the radius of convergence. So basically, if you have a, let's just kind of look at on the number line, if you have A here, and for X in this part, so let's see, this is distance R from A. So this is the x-axis, and this is also distance from A. So for any X value between them, so for X minus A absolute value less than R or equal to, I probably should exclude this for this particular example. In this case, if the series is convergent for X minus A less than R, so if series is convergent for X minus A is less than R, we talk about this part of X value, right? So the R is what we call the radius of convergence. It just basically means how far away from A is the function, it's the series going to be convergent. The interval of convergence is the interval of X values for which the series is convergent. And in the diagram, in the number line I have above, it's all the part that shaded in green, right? So that will be called the interval of X values. But what are they? You can actually find them because this is A is in the middle. So the lower end is always going to be A minus R. The high end is always going to be A plus R. So for the interval A minus R to A plus R, so that will be the interval that the series is convergent. So this interval is what we call the interval of convergence. So there are two terms. One is the radius of convergence, it's just the R value. One is the interval of convergence. You have to write down the interval of X values. It's always from A minus R to A plus R. So those are the terms. Let me make a table for all three cases. Hopefully it's not going to be that confusing. So case 1, so series converges at, so case 1 is the series converges only at a particular value X equals A. And then the radius of convergence because it's only one number, right? So the R value is just going to be 0. There's no kind of distance from A that give you X values for the series to converge. It just only at that particular A. So there's no sort of radius there. and the interval of convergence will just be, it only has one value, so we're just going to put a in a curly bracket. It's not an interval, it's just one element there. So that's the first case. The second case says the series is convergent for all x values. In that case, the radius of convergence is just including all numbers, right, on the number line. So the radius is just going to be infinity, from 0 to infinity, 0 to negative infinity, including all x values. And the interval of convergence will be from negative infinity to positive infinity. So that will be the interval. And the third case saying that the series converges for x minus a is less than r. If you have this case, then the r will be the radius of convergence, and the interval of convergence will be from a minus r to a plus r. Now, I want to point out that that's one case, but you could also, in this third case, third possibility, you could also have a bracket here on the left. It might including a minus r, that doesn't include the other side. You could have the other way, doesn't including the left side, but including the right side. So you have to be very careful here to decide which end of the interval is included. Or maybe both of them will be included. So when we talk about the interval, even though you know the radius of convergence is r, but you have to be careful, see if the two endpoints of the intervals are included or not. So that's more possibilities there. So that's a radius of convergence and the interval of convergence. Any questions on those I guess definitions? And if you want to find the radius of convergence, it's always better, if possible, try to reach this expression, because from there you can immediately tell what r is, right? And then you can tell what the interval is, but you have to do a little bit more work, obviously. But try to get to this this expression if possible. If you don't have any questions, I'm going to give you 2 examples. So the exercise is to find the radius of convergence that's the first thing, and also we're going to find the interval of convergence. We're going to find 2 of those for the series given. The series given is sigma n from 0 to n to infinity, right? Negative 3 raised to the power of n, x to the n, divided by square root of n plus 1. Basically taken directly from, this example is taken directly from the book. So the first thing we're going to do, if we want to know the radius of convergence, we need the r value, and the interval of convergence, we need to know all the x values, right? So the first thing we're going to do is that we're going to just follow what we did. So we're going to use the ratio test here. by defining L equals limit n goes to infinity of an, so that's a -3 to the n plus 1, x to the n plus 1, divided by square root of n plus 1 plus a 1, so n plus 2, and then divide by -3 to the n, x to the n, and then divide by square root of n plus 1. And again, I'm going to try to simplify. In the process of simplifying, I'm going to separate the numerator terms and then make it into -3 to the n times -3, and then multiply by x to the n times x, and then divide by square root of n plus 2, multiply by the reciprocal, which is square root of n plus 1 divided by -3 to the n, x to the n. And by doing this, we can cancel a couple of terms, -3 to the n, x to the n, and put together everything else like we have done before. So that will be limit n goes to infinity of absolute value square root of n plus 1 divided by square root of n plus 2 times, I'm going to close the absolute value and then put the -3x, I'm going to put it aside, times absolute value -3x aside, because that doesn't depend on n. And from here, we're going to take the limit as n goes to infinity. In the first absolute value in the square root, the numerator and denominator, I'm going to divide by n, right? And that will become just limit n goes to infinity of square root of 1 plus 1 over n divided by square root of 1 plus 2 over n. As n goes to infinity, both square roots will give you 1. And then the -3x just become +3x in the absolute value, but we can just leave it there or pull out the 3, doesn't matter which one you do at the step. So this part approaching 1 over 1, and then the 3x becomes 3 times absolute value of x. 3 is positive, you can put out, but x, we don't know, it could be negative, so we have to keep it inside. So that's what L is. And we want to find the radius of convergence under the interval, so we want it to be convergent, right? So we set this as less than 1. And then divide by 3, so that will be absolute value of x. So 3 absolute value of x less than 1. So absolute value of x is less than 1/3. There you go. You can treat this the form that I highlighted earlier. So that's in the form of absolute value x minus 0 less than 1/3. So we have, this is the r value, this is the a. So we want it to be x minus a less than r, right? So that's what we want. So we have it. So therefore, the radius of convergence is 1/3. You can write as r equals 1/3. Just 1/3 is fine. How about the interval? Well, that, if you remember what I wrote, it's just going to be 1/3 away from the a. So a is 0 here. And the I is 1/3, it's just going to be 1/3 to the right and the 1/3 to the left. So that will be -1/3 to +1/3. So that will be the interval. if you think about it, right? So this is a minus r and a plus r. But be very careful. If you recall the table I wrote for the last case, we don't know, even if we write down the interval a minus r to a plus r, but we don't know if the ends are included in the convergence part. So we still have to do a few testing. So still need to know if the series is convergent at negative 1/3 or positive 1/3. We still have to test those two endpoints. It's definitely convergent in the middle between them, but at the ends, we don't know yet. So let's test them. So to recall the series that we given is, let me write down -3 to the n. X to the n divided by square root of n plus 1. That's a series. And we're just going to want to know if it's convergent when x equals negative 1/3. So at x equals negative 1/3, we're going to plug it in. The series becomes n from 0 to infinity, -3 to the n times negative 1/3 to the n divided by square root of n plus 1. And then that we can combine the numerator because both has the exponent n. So that's a series, -3 times negative 1/3 to the n and divide by square root of n plus 1. So that's a series. -3 times negative 1/3 is just 1. 1 to the n is just always a 1, just 1 over square root of n plus 1. Is this convergent or divergent? Well, I don't know, but I can, because the denominator has two terms, n and 1 added, so I can use comparison test quickly. So that's going to be less than or equal to series 1 over square root of n, which is 1 over square root of n. We know this is a 1 over n to the half. We can use p-series test to find out that that's actually divergent. Oh, you know what? I'm messing up, didn't I? I messed up, sorry. Because that's not helping us. The bigger one is divergent, it doesn't help us. Sorry about that. So that's, I'm just gonna write as, so sigma n from 0 to infinity. So at this point, I think I'm going to use a substitution. We haven't really done that, but I think it works. So use u equals n plus 1. So n equals u minus 1. So I'm going to substitute into the series here. So that will give me sigma infinity, and then n equals 0. So that becomes a u minus 1 equals 0. Just replace the n there. And 1 over square root of u. So that will be series u minus 1 equals 0. That's a u equals 1. And the infinity, so you get 1 over square root of u. So they're equivalent. And then this one we know it's definitely divergent using p-series test. So the series, when x equals negative 1/3, is divergent. at x equals -1/3, the series is divergent. That means we're not going to including -1/3. How about 1x equals 1/3? So the series becomes n from 0 to infinity, -3 to the n times 1/3 to the n divided by square root of n plus 1. And then that will become series -3 times 1/3, that's -1 to the n divided by square root of n plus 1. And it turns out that this is the alternating series. And if we perform the alternating series test, this is going to be convergent using alternating series test. I hope it's okay if I don't do that. If you want to use alternating series test, you have to write this as -1 to the n, 1 over square root of n plus 1. And then we're going to call this Bn. You have to do two things for alternating series test. The first one is you take the limit to show that as n goes to infinity, Bn goes to 0. That's the first one. The second one, you have to show that Bn is greater or equal to Bn plus 1. So those are the two conditions of alternating series test. So we found out that when x equals 1/3, the series is convergent, but when x equals -1/3 is not convergent. So therefore, the interval of convergence is, we're not including -1/3, so parentheses -1/3, but we have to include +1/3, so we put a bracket there. So that's the interval of convergence. So it's a lot of work, and then I'm not going to say it's easy. It definitely could be confusing. But the first thing we do, we try to find the radius of convergence. So we try to find out something looks like x minus a less than r form that will give us r value. Okay, so that's what I did by using the ratio test at the beginning to try to end up with x minus 0 less than 1/3. So that's like sort of the first big chunk of the process to find the radius of convergence. And then we can definitely find the interval, but the interval we have to be very careful at the endpoints. Even though we find the interval, but it may not be the accurate one, right? We have to consider the endpoints. So that's what we did. We have to take each endpoint, each x value, plug into the series, see if it's convergent. So that's the second big part. So 2 parts, a lot of work. Questions on this example? So as you leave today's lecture, I hope that you feel comfortable, or at least may not feel comfortable, but at least keep in mind that you have to know the difference between power series and then the series we talked about before. It's just power series involving the powers of x raised to a power, right? And also you should keep in mind that there's a difference between radius of convergence and interval of convergence. there's more work involved to find interval of convergence. Any questions before I move on? So like when there's another variable, that's the one we use power series. Right, when you have a series, you have like a sigma n from one value to another value, but inside the sigma notation, you have x in it. And sometimes it could be y, or instead of x, it could be z. Right, so that's what we call power series. When you expand it, you have x raised to powers, right? So the example I had earlier, what was it? This one. So if we were to expand this, let's see n equals 0, we put in there, right? We get -3 to the 0, which is 1, divide by 1 plus 0 plus 1 square root, that's also 1. And then x to the 0 is also 1. So we get 1 plus, if we put 1 there, we get -3 divided by square root of 2, and then x. And then if we put 2 there, we get -3 squared, which is 9, divided by, what did I say, 2? So square root of 3, and then x squared. So as you can see, when we expand it, we get a sum of x terms, like x to the first power, x to the second power added together. So that's a power series. It's a series of power functions. If you remember that power functions are just x to a power, right? So it's you take those power functions, you add them together. Good question. So let me do one more example, then I'm going to stop on this section. So the next example is we have sigma. Again, we want to find the radius of convergence and the interval of convergence. So the example is n from 0 to infinity, n times x plus 2 to the n, divided by 3 to the n plus 1. So for this, so find radius of convergence and then also interval of convergence. So again, I'm going to try to use the ratio test. I'm not expert in this material, but it looks like a ratio test works well in many times. Again, it's not the only test that works, right? You could try other ones. But ratio tests seem to work a lot easier. So I'm going to say L equals limit n goes to infinity, absolute value. So that's n plus 1, parentheses, times x plus 2 raised to the power of n plus 1 divided by 3 to the n plus 1 plus 1 divided by n times x plus 2 to the n divided by 3 to the n plus 1. And again, just like I have done before, I'm going to simplify this in the absolute value. So that's a limit n goes to infinity, absolute value, n plus 1 is just n plus 1. And then x plus 2 to the n plus 1, I can write as x plus 2 to the power of n times x plus 1. Sorry, x plus 2 to the first power. And divide by 3 to the n plus 1 plus 1, I'm going to write as 3 to the n plus 1 times 3 to the first power. The reason I'm leaving it there because I know the denominator have a 3 to the n plus 1 that can cancel. You could write as 3 to the n times 3 squared. That's perfectly fine, but you don't have to write that way. Multiply by 3 to the n plus 1. Oops. And the denominator we have n times x plus 2 to the n absolute value. So now we can simplify 3 to the n plus 1. Oops. And we can also simplify x plus 2 to the nth power. And the rest, just like I have done before, I'm going to put the parts that with n together, and then the part that doesn't have n, I'm going to put it aside. So that becomes the limit n goes to infinity, absolute value n plus 1 times x plus 2. Denominator, I have a 3 times n, so I'm going to put n on the left, 3 on the right, but it doesn't matter. I just want to group the 3 with x plus 2. And separate them, so that's a limit n goes to infinity of x n plus 1 divided by n, absolute value, times another absolute value, x plus 2 over 3. The 3 you can put in the absolute value in the denominator, but it's positive already, so you don't need to include the absolute value for 3. And if we take the limit here, this part, we just, like we have seen before, right? We divide by n to all terms, and then take the limit as n goes to infinity. It turns out that that is just 1. So we end up with just 1 times x plus 2 absolute value over 3. That's what L is. But if we want it to be convergent, right, we want to find the x values that will make it convergent. So that means we have to make sure that this expression we found at the end is going to be less than 1. That's just because we have a ratio test. So what do we have from there? We have x plus 2, absolute value less than 3, right? If we multiply by 3. Now, this is not in the correct form, so you have to rewrite it as x minus a less than or equal to something. So that's the absolute value x minus -2 less than 3. From this form, this is R value, this is A. A is -2 and I is 3. So therefore, we have radius of convergence is R equals 3. Why do we have to put it in this form? Because to get A, if you go back to what I highlighted right earlier, go back to the very earlier. So in the theorem, it says the series converges if x minus a is less than R, right? So it has to be x minus a is less than R, not x plus a, right? And the a is the sort of the center of convergence. And then R is how far away from A is x going to be convergent. So it's always easier if you put in the x minus a number, x minus a less than R form. Then you can just pick the A directly from there and pick the R value from there. So that's what I did. I have to put it as x minus a number. So the radius of convergence is 3, right? How about the interval? Interval of convergence. We know for sure it's going to be A minus R and A plus R. But then we always have to be careful to check the endpoints. Because the endpoints could be included in the convergence interval. So in this case, A is -2. So we have -2 minus 3 and the -2 plus 3. A is -2, right? So that will be from -5 to 1. This is the interval. in the middle is definitely going to be convergent, but what about -5 and 1? So that's what we have to check next. So check at x equals -5, is it going to be convergent? I don't know, let's plug it in, right? The series I had, so the series I had was n from 0 to infinity, n times x plus 2 to n divided by 3 to the n plus 1. But for now, I'm going to put -5 in there. So if I put -5 in this for x, so I get series n from 0 to infinity, and -5 plus 2, that's a -3 to n, and divide by 3 to the n plus 1. Okay. And that I can simplify, even though it looks complicated. I mean, you could definitely use the ratio test to find out, right? But let's kind of simplify this. So that will be n from 0 to infinity, n times the denominator I'm going to rewrite, but the numerator I'm going to leave it the way it is, -3 to the n for now. And the denominator is 3 to the n times 3. The reason I'm doing this because I want this part to be able to put it together as one fraction raised to the n. So I end up with this 3, I'm going to bring it outside, so I get 1/3 sigma n times -3 over 3 to the n, which is just -1. So I get 1/3 sigma -1 to the n times n. But is this going to be convergent or divergent? You can use, it's an alternating series, right? You can use alternating series test if you like. So use alternating series test, or just expand it and look for the patterns if it's obvious. So if you use alternating series test, if you take the limit n goes to infinity of bn, is that going to be 0? And the bn here is just n. This is a bn. And if you take the limit as n goes to infinity, that's going to go to infinity. It's not going to be 0. So it's from alternating series test, it's not going to be convergent. It's divergent. So when x equals -5, we get divergent series. What about x equals 1? Again, you can put it in there. And from 0 to infinity, and x is 1, so we get 3 to the n divided by 3 to the n plus 1. Do the same trick. Combine the 3 to the n terms. So we just end up with sigma n times 3 to the n divided by 3 to the n times 3. So that's just sigma n over 3, or 1/3 sigma n. This is just, we're adding the integers, right? From 0 to 1, add 0, 1 to 3, all the way to infinity. And that's going to be divergent as well. So it turns out that in this example, both endpoints, -5 and 1, I probably should label it at x equals 1. Both endpoints will give you divergent series. So they're not in the interval of convergence. So therefore, the interval of convergence is just from -5 to 1, and it does not including the endpoints. They're not included in this case. So we use parentheses. Okay, so that's all I have. I don't have anything else. If you have any questions on what we do today, or about the exam or the quiz. If not, I'm going to let you go. I'll see you on Wednesday. Take care.